Thank you. So I'd like to thank the organizer for giving me the opportunity to be here, and thank my advisors in Dean Jadley for the advertising in this lecture last week, and to wish him a happy birthday. So I have to... So this is the outline of my talk. So I will first remind you some result on curvature, pinching, and rigidity of Riemannian manifolds. Then I will present an alternative proof based on a fourth-order geometric flow of integral pinching. And I will give some ideas of the proof of this result. So first of all, I begin with the classical result of Hamilton. So it was the beginning of geometric analysis. So he used the Ricci flow to show that for a three-dimensional compact manifold, if you start the normalized Ricci flow with a metric with positive Ricci curvature, then the flow will exist for all time, and it will converge as the time goes to infinity to a metric of positive constant curvature. And so it tells you that your manifold is diffeomorphic to a quotient of the sphere. So one question that is natural to ask giving this result was, is it possible to generalize such a result in higher dimensions? So, for example, the result with the assumption Ricci positive is false for n greater than 4, so it's not the good condition to impose to have a similar result in higher dimensions. And so there has been a result of Hamilton for four-dimensional manifold, assuming that the curvature operator, seen as an endomorphism of lambda 2 of M, is positive. So it's a positive endomorphism. And then you have a similar result. The normalized Ricci flow exists for all time, and when t goes to infinity, it's converged to a metric of constant positive curvature, and then your manifold is diffeomorphic to the quotient of a sphere. So this result was extended recently by Bohm and Wilking to all dimensions. And the idea to prove this result leads to the well-known differentiable sphere theorem for 1/4 pinch manifolds by Wendell and Schoen, that say that if the sectional curvature are pinched, the maximum over the minimum over the maximum is less than 1/4, then your manifold will be differentiable, will be diffeomorphic to the sphere. So there has been another result that has been given before by Risken. So it was for all dimension greater than 4. And the pinching assumption is the one that is written here. So I recall the decomposition of the curvature tensor. So you can always write the curvature tensor as a wide part that is totally trace-free, plus a part that was like this, plus a last term that involves the scalar curvature. So here, this is the traceless Ricci tensor. And so it's an orthogonal decomposition. So you have, you can write the norm of it as this. This is a traceless Ricci tensor plus 1 over 2n n minus 1 scalar curvature square. So to have this written in this way, I write the norm of the curvature tensor when it's seen as an endomorphism. So it's 1 over 4, the classical norm for 4-0 tensor. So you have this decomposition, the curvature tensor. So this one is equal to 0 if and only if G is locally conformally flat for n greater than 4. And this one is equal to 0 if and only if your metric is Einstein. So in particular, for the case of the sphere, your manifold is locally conformally flat, is Einstein, so the two terms here are 0, and you only have the remaining term, which involves the scalar curvature. So the pinching here says that you're not too far from this situation. The Weil part and the traceless Ricci part are small with respect to the scalar curvature. So the constant delta n that is here is given explicitly by a formula depending on the dimension. So I gave it for n equals 4, for example. And you have the similar result, that is that the normalized Ricci flow exists for all time, and it converges when t goes to infinity to a quotient of the sphere. So in 1998, Margerin gives the sharp constant in the case of 4-dimensional manifolds. So if you take 4-dimensional manifolds and you assume this pinching, so with the constant equals to 1 on the right side, then you have the same result, but this condition is sharp. That means that if the equality holds in this pinching, then you will be. So Margerin said that if you have this condition, and positive scalar curvature, then M is diffeomorphic to S4 or RP4. And he also said that, so the equality case is completely solved. So equals the same thing. And this, then Mg is diffeomorphic to CP2 or a quotient of S3 cross S1. So this gives kind of sharp answer to the question in dimension 4. And the question is how to give another result in this direction. And in fact, oh, that's not the. So an idea of the proof of this result, in fact, you only have to suppose that this is true in a weak sense, not in an average sense. I will talk about this later. So the proof of this result so of all the results I just presented, follow some strategy. It consists in applying the Ricci flow to the initial metric under the assumption of pinching and the curvature, to apply the maximum principle to show that the pinching is preserved along the flow, and to apply the maximum principle that to show that the pinching becomes better and better along the flow so that it will converge to a metric of constant constant sectional curvature. So this was the strategy to prove all the results I stated before, with more and more difficulties to solve to get better results. So, in fact, you only have to suppose that the pinching is true once you integrated it. So if you only suppose that you have this, and you replace the assumption of positive scalar curvature by its conformal counterpart, that is the Yamabe constant is positive, then you have the same result. Your manifold will be diffeomorphic to S4 or to RP4. And you also have the equality case. If you suppose that you have this weaker pinching, so it was the same thing but integrated, then you will be conformally diffeomorphic to CP2 or to a quotient of F3 cross S1. So I just recall the definition of the Yamabe invariant. So if you take a complete manifold, it's defined to be the infimum of this quantity. So nebula u square plus n minus 2 over 4n minus 1 square with u in I2 and the norm in L to n over n minus 2 equals to 1. And in the compact case, as this is the scalar curvature under a conformal change, it's the infimum of the normalized mean scalar curvature over the conformal class of G. So you have to normalize it by the volume. So it's power 2 over n. So this is if n is compact. So one of the interest of this theorem is that it is conformally invariant. The assumption, according to the Gauss-Bonnet formula in dimension 4, it will remain after a conformal change on the metric, and the assumption of positive Yamabe constant also remains after a conformal change of the metric. So you can perform a conformal change on the metric before starting the flow. So the idea to prove this is to get the pinching of Marjan, the pointwise pinching. So I just finished with the Yamabe invariant by saying that it is positive if and only if you have a conformal metric that has positive scalar curvature if M is compact. So according to the Gauss-Bonnet formula, I will write it down here. You have that So it was less Ricci tensor plus 1 over 24. Titular curvature is a topological invariant in its 8 pi square, the characteristic of M. So if you put this formula together with the pinching, you get this equivalent pinching. So the while functional that appears in the left is a conformal invariant, so you can do a conformal change, and they study a fully nonlinear equation to prove that, in fact, there exists a conformal change on the metric such that the pointwise pinching is satisfied. Then you can apply the result of Margerin that say that your manifold is diffeomorphic to a quotient of the sphere. So the question that I will ask is it possible to obtain the same kind of result that I stated in the beginning? That means that if you have your integral pinching, then you apply a geometric flow. The flow will exist for all time and converge as t goes to infinity to a metric of positive constant curvature. So one of the problems that will appear is that you cannot apply the maximum principle to show that your integral pinching will be preserved along the Ricci flow. It works very well for pointwise pinching, but it's difficult to keep such a pinching along the Ricci flow. So what I will present is a proof based on another geometric flow that will be a fourth order flow, and that has this property of preserving such an integral pinching along the flow. So we'll define this functional, and to perform its gradient flow. So the interest of doing this is that along the gradient flow, the curvature will decrease. The functional will decrease. So if you start with a negative value of the functional, then it will remain negative. So if the pinching is given by this quantity being negative, then along the flow it will stay negative, and you can expect to have the convergence to round metric at the end. So the theorem is the following. If you take a 4-dimensional manifold with positive Yamabe constant, and if you assume this pinching, then the solution of the gradient flow of F will exist for all time and will converge to a metric of constant sectional curvature. So in fact, the 1/2 here is just to compare the result with the other one I stated. We will prove it with 5/16 instead of 1/2, and it's a stronger result than this one. So I will describe a little bit such fourth order curvature flows that are given by the gradient of functional that are quadratic for the curvature. So the first thing to notice is that in dimension 4, these functionals are scale invariant. So if you scale the metric, your functional won't change. This is because 2 is equal to 4/2. Yeah, the functional that is scale invariant in dimension n is the n/2 norm of the metric, the curvature. So this will be very important in our study and explain that it only works for 4-dimensional manifolds. And it also gives you, so as the functional will decrease, it will give you a L2 control of the curvature. And in dimension 4, L2 control, if you have an L2 bound on the curvature, it will give you a control of the geometry. If it would be in higher dimension, you would have to control the n/2 norm of your curvature. So the study of such flows it begins with there was an article by Zheng Liu. I think it was in 2003. So it was for the gradient flow of the Ricci curvature in dimension 3. And then street studies, so in 2008, 9 and 10, the gradient flow for the full curvature tensor. And so they prove small time existence and integral estimates for such flows. So what is the gradient flow for this functional? So first of all, the gradient of the functional is given by this formula. So if you take the first variation of your functional, you can express it as a scalar product with in L2, and the term that appears just here is called the gradient of the functional. So for this particular functional, it is given by such a formula. So the first term is the most important one. So it's minus a positive constant time Laplacian of Ricci. Then you have two other terms that are also of fourth order, but you can, if A is not too big, it won't gives problem in your study. And the last term is a quadratic term of the curvature, and so it's a lower order term. So the equation we will study is this one. So the derivative of the curvature is given by minus the gradient of your functional, and the initial metric is given by some G0. So the first question to ask is, do we have small time existence for such flows? So it's given for something like that plus some other terms, and G0 equal G0. And so you have the same kind of problem that are arising than for the Ricci flow. That is that the operator given by the gradient is invariant by diffeomorphism, so it won't be elliptic, and you apply the deterk trick to find solution of it. The only thing to check is that these terms here won't make the operator to become non-elliptic. And if A is not too big, it will be okay. So, roughly speaking, the Ricci flow is the derivative of G is minus Ricci, and you know that if you linearize the Ricci tensor, you get something that it looks like the Laplacian after applying the deterk trick. Here you put Laplacian before, and so it will give the an equation like the derivative of G is something like the B Laplacian of G, once you have linearized your operator. So after applying the Dieter trick, it will become a strongly parabolic equation. And according to the theory for this kind of equation, you will have existence and unicity on a short time interval. Then you can you have a maximal solution. You know that your solution will exist for a maximal time interval, and for some t that is positive, the flow will stop existing. So you have something like that. And so you start from G0, the flow exists, and either it exists for all time or it stops at some finite t, and then you have a singularity, and the game is to understand what's happening here when you get a singularity. So I just remind you a few facts about the Ricci flow. So for the Ricci flow, you have derivative estimates on the curvature. You know that if the curvature stays bounded by some constant, then all the derivative of the curvature will be bounded. So I will put a 2 here. So by some constant depending on k, on t and d, or t over k, on t in 0t. So this kind of estimates can be obtained by applying the maximum principle to the curvature. And it gives you the nice result that if the flow stops existing, then you know that the curvature blows up. Because if it stays bounded, that all the derivatives stays bounded, and you can continue the flow over t, after t. So here we have a fourth order equation, and you don't have any maximum principle that can apply because it's, well, really peculiar to the dimension, to the second order equations. So we can't have such estimates only by applying the maximum principle. And so we will have to use integral estimates. That means that we estimate the curvature, the derivative of the curvature, but only in an L2 norm. So we have the following result. So it's very similar, but it's not a pointwise estimate, but an integral estimate. And so we wish to have the same kind of result as in the Ricci flow, meaning that if the flow stops existing at some finite t, then the curvature will blow up. So the problem to have this result is that once you have your integral estimates, so once you have that this is L2 is true, you want to get CK estimates, real estimates as in the Ricci flow, and you will get it by Sobolev inclusions. So you know that you have this inequality. So you can control the LP norm from the HK2 norms. Once you have one inequality like this, you can prove all the Sobolev inequalities, and then you can deduce pointwise estimates on the curvature from integral estimates. The thing that can happen is that you don't have the control of your constants A and B along the flow. So it can happen that your Sobolev constants are going to infinity, but your curvature stays bounded. So we will define the following Sobolev constant. So if you look at this inequality, it will be true. You know that there exists some B such that this inequality will be true as soon as A is taken large enough. So if you take a good A for a compact manifold, you know that there exists some B such that the inequality holds. So the constant BA of G is a better B such that this inequality holds for the A. So this is for compact manifold. For complete manifolds, you have to assume some geometric restriction on your metric so that such an inequality will hold. So we define this constant, and if the set here is empty, you just say that the Sobolev constant is infinite. So now we will know that if you can control one of these Sobolev constants along the flow, then you can get CK estimates for the curvature, and then you will know that the curvature blows up. So the thing that has to be understood now is what happens if the Sobolev constants are going to infinity. And we can say, we will state this definition. So if you take a family of complete metrics, so on a manifold that is not necessarily compact, with the curvature that is uniformly bounded in a C0 sense, then the first two assertions are classical. That is that having a lower bound, a positive lower bound on the injectivity radius is equivalent to control the volume of unit balls if the curvature stays bounded. And in fact, it's also equivalent to having control on some Sobolev constant. That means that if you have a control on the curvature and the volume of small balls, you can prove a Sobolev inequality. And if you have a Sobolev inequality, then your injectivity radius is positively bounded from below. So if one of these conditions are satisfied, we will say that the family collapses with bounded curvature. And now we can say that if the flow exists, the maximal solution of the flow exists at some time interval 0 t, if it stops existing at t, then either the curvature blows up or the curvature stays bounded, but the manifold collapses. The injectivity radius is going to 0. So the second case doesn't occur in the Ricci flow. For the Ricci flow, you know that if the curvature is bounded, then at a singular time, you know that the curvature blows up. You don't have this phenomena of collapsing with bounded curvature. Here, we can't rule out this kind of singularities. We don't have any example of such a singularity, but it is still possible that your curvature stays bounded along the flow, but your injectivity radius is going to 0. So we want to rule out this case because when the curvature blows up, we know what to do. We will make a blow up with scaling the metric and see what happens on the limit. If the manifold collapses with bounded curvature, it will become much more annoying. You don't know what is happening. Your manifold will shrink to some manifold with less dimension, and you don't know how to handle this case. So a solution to get rid of that is to control the Yamabe constant. In fact, if you have a lower bound, a positive lower bound on your Yamabe constant, then your family of metric won't collapse. So it was used, this kind of thing was used by Akutagawa. I don't know it. He's the first one. So this comes from the fact that by the definition of the Yamabe constant, it gives you some Sobolev inequality. You can write that so in dimension 4, so this is n 2n over n minus 2 is less or equal than, so times the Yamabe constant, is less or equal than the integral of this. Here you have a 6. I forgot. Plus 1 over 6, the scalar curvature times u squared. So you can write it this way. And if your scalar curvature is bounded in the C0 sense, it will exactly give you a Sobolev inequality as soon as you have a positive lower bound on the Yamabe invariant. So this is why you have this result. If you can control the Yamabe invariant from below, then you won't have collapsing. So I remind you that in the assumption of the theorem, you had that the initial metric was with positive Yamabe constant. So now we have to know that this assumption will be preserved along the flow. So to see that, we will use that we always have this inequality. So I try to explain it. So the left side is Yamabe constant to the square. The right side is the mean Q curvature. So the Q curvature is given by this plus 1 over 24, the scalar curvature to the square, minus 1 over 2, the traceless Ricci curvature. And it's associated to a conformally covariant operator. So it behaves well under conformal transformation. In fact, once you integrated it, so it's equal to 1 over 24 the scalar curvature to the square minus 1 over 2 the twice Ricci tensor to the square, and it is conformally invariant. And you can also remember that in the Gauss-Bonnet formula, it can be written like that. So it's a term that's not the Weil term in the Gauss-Bonnet formula. So in this inequality, both terms are conformally invariant, so we can perform a conformal change on the metric to show it. So just take a Yamabe metric. So you take J tilde in the conformal class, that is a Yamabe metric. So it will achieve the minimum of the Yamabe functional, Yamabe metric, and it will be a constant scalar curvature. So now you can write that. So the Yamabe constant is 1 over 6, 1 over the volume to the power 1 over half, the mean scalar curvature. So if you take the square of this, you will get 1 over this times the volume times this to the square. And now, since the scalar curvature for your Yamabe metric is constant, you can write this as 1 over 36 the volume times the scalar curvature to the square, and that's exactly the integral of Rg tilde to the square. So this is greater than 2 over 3 times 1 over 24, the scalar curvature, minus 1/2 of the twice Ricci tensor. So it's greater than this. So this is true for your Yamabe metric. You have two quantities that are conformally invariant, so it's also true for your metric. So the last thing we have to check is that the mean Q curvature will stay positive along the flow. So this is given by our pinching. So we had this functional f of g, so it's equal to y to the square plus 5 over 16 minus 1 over 8 times 24 square. So the derivative of it is given by the gradient of f scalars the derivative of the metric, which is taken as the gradient of f. So it's negative. So as I said before, the pinching will be preserved. If you start from a metric with negative functional, then it will stay negative. And you can write that so f of g is negative, so we'll say that it's less than minus epsilon, and you make appear the Q curvature. So here you take 1 over 4, the traceless Ricci, and this is less than 1 over 8, so 1 over 24 this, minus 1 over half, 1 over 2 this. So this is the mean Q curvature. You have a minus epsilon here, so you can put it here. And it tells you that the mean Q curvature is always bigger than epsilon. So you know that the functional will be less than a negative constant, then the Q curvature will be uniformly positive along the flow. So the inequality that is just there gives you that if you start with a positive Yamabe invariant, it will stay positive and bounded by a uniform positive lower bound. So with the lemma just here, you know that the manifold won't collapse, so you don't have the second case in the result I stated before. You know that as in the Ricci flow, if the flow stops existing for some finite t or infinite t, then the curvature will blow. No. For some finite t, then the curvature will blow up. And it's t is infinite. You don't know whether the curvature blows up or not, but you know that the manifold won't collapse because of this. So once we know this, we will make a blow up. So the idea is the same as for the Ricci flow. So you have existence on a time interval. Here you have some manifolds with a curvature blowing up. So we take a sequence of time such that the curvature blows up and a sequence of points where the curvature is maximal. So the xi is points of larger curvature in the manifold, and these are time ti. Then we normalize the metric, so we dilate it by the curvature. We look at it like this. So the GI are the rescale metric. This is GI, this is GTI. And now, so you know that because of the rescaling of the metric, they will all have bounded curvature. So the curvature of GI is less than 1, and you have one point, xi, where it is equals to 1. You also know that the Yamabe invariant is uniformly bounded from below by a positive constant, because you just rescale your metric, and the Yamabe invariant being a conformal invariant, it is scale invariant. So you have a bounded curvature and positive Yamabe invariant, so you know that it won't collapse. And in particular, it won't collapse with bounded curvature. And in particular, you have Sobolev constants, so you can get CK estimates from the integral estimates. So once you know this for the rescaled metric at a singular time, you also know that all the derivatives of the curvature are bounded. And that it won't collapse with bounded curvature, so the injectivity radius for the metric GI is greater than some I0 strictly positive. So you can now apply a compactness theorem of Hamilton, like in the Ricci flow. All the derivatives of the curvature are bounded, the injectivity radius is bounded from below, so you can pass to the limit and get some complete manifolds. So the rescaled metric are still solution of the flow, and the pointed manifolds M, Gi, Xi converge to some complete manifold M infinity, J infinity, X infinity in the C infinity pointed topology. And this limit will have some nice properties. So it will be non-flat. It will be non-flat, that's because of this. You know that at the point X infinity, the curvature is equal to 1 in norm. It will have positive Yamabe constant. You can see that the limit. And it will have the nice property of being critical for your functional. This is because the functional is scale invariant. You can see this by a change of variable. So now you know that you have some singularity model. That means that when your flow stops existing, if you zoom at the point where the curvature blows up, you know what the singularity looks like. It looks like a critical point for your functional. And so it's similar. It plays a similar role to Ricci soliton for the Ricci flow. So now we have to understand what kind of singularity can happen and what can not happen. So what we will do now is to prove a pinching result on the limit manifold. And such a result is easier to prove because you know that the limit manifold is critical for your functional. So it gives you more information. You know that the critical manifold, the limit manifold will satisfy something like that. And under this assumption, we can prove a pinching result for the limit manifold. So first of all, we show that the pinching we have along the flow pass to the limit in some way. So if you have the first inequality, it will be true along the flow, and then by this calculation here, you see that, so this is the first term in the second inequality. So it's less or equal than 1/8 the mean Q curvature, and we saw that it less or equal than 3 over 2, the Yamabe to the square. So it will give 3 over 16, the Yamabe constant to the square. So along the flow, you will have this pinching with the Yamabe constant. As it is scale invariant, the rescaled metric will satisfy the same pinching, and you can pass this pinching to the limit. The one that is the first one won't pass to the limit because you only look at the neighborhood of a point in your manifold when you do the blow-up. And once you know this for the limit manifold, we can show this rigidity result. So if you have a metric that is critical for the functional, that satisfies this pinching with positive Yamabe invariant, the limit also has positive Yamabe invariant, and an assumption of bounded L2 norm of the curvature that is granted because it's true along the flow. And then you prove that G is of constant sectional curvature. So this is doing by studying this equation. You can you integrate this. You do the scalar product with Ricci, with the traceless Ricci tensor. It will give you an inequality, and then you can prove such a result. So if we come back to what we had, we took a limit, it satisfies this pinching, and it's critical, so you know that the singularity model under our pinching assumption will be of constant sectional curvature. But you also know that its volume is infinite. That's because under the flow, the volume stays constant. The flow is of the volume of the manifold stays equal along the flow. That's also because the functional is scale invariant. So when you rescale the metric, you will get an infinite volume manifold, and under the assumption that the scalar curvature in L2 norm is bounded, and of constant curvature, your curvature has to be 0. You have constant scalar curvature bounded into L2 and volume infinite, so the scalar curvature has to be 0, and so your limit manifold has to be flat. So what we prove here is that the blow-up at a singularity will be a flat manifold, but since there's a point where the curvature is equal to 1, it gives you a contradiction. So under the assumption of the pinching, then you can't have a singularity. So you know that the flow exists for all time. You won't have a finite time singularity. And in fact, you won't have an infinite time singularity. If the flow exists for all time and the curvature blows up at infinity, you can do the same thing. You rescale, you pass to the limit, and you show that the limit is flat, but it can be flat, so the curvature stays bounded along the flow. So the only thing we have to prove now is that it will converge to a metric of positive constant sectional curvature. So since we have a gradient flow, the derivative of f is given by the L2 norm of the gradient of your functional. If you integrate, it gives you this equality. And it's by the Gauss-Bonnet formula, it's not difficult to see that the functional f is minorated from below by minus p squared, the characteristic of your manifold. So this equality gives you that this is bounded for all t. So this integral here have a limit, a finite limit, when t goes to infinity. So this has a finite limit when t goes to infinity. So as this is finite, you can you know that there exists some sequence of time such that this quantity goes to 0. So you take such sequence of time, you take the associated metrics, and so the GTIs, and we want to pass to the limit. So it has bounded curvature, because you have no singularities. It has a Yamabe invariant bounded from below by a positive constant, so it won't collapse. And with your estimates, it has bounded CK norm of the curvature. So you can pass to the limit for this GTI, and as this goes to 0, the limit manifold will be critical for your functional. Here you don't rescale your metric, so the limit will be compact manifold. So the GTI converges to a compact manifold, which is critical for the functional f, and that satisfies this pinching here. So you can apply the lemma, the rigidity lemma for critical manifolds, and it shows that the limit is a metric of constant sectional curvature. So you can find a subsequence of time such that the flow converges to a manifold of constant sectional curvature, so of positive constant sectional curvature because the Yamabe invariant is positive, and then it will be a cushion of the sphere, so S4 or RP4. Thank you for your attention.